Okay. Can you see the screen?
Yes, sir.
Okay, all right. We are ready. Should I go ahead?
Yes, sir.
Okay, very good. So once again, very good morning, and I hope you are seeing the title of this talk, which is Past, Present, and Future of Physics Computing in India. I thought that when I am talking to a young audience, like the one which is sitting in front of me, students who are into physics, they are fascinated by physics, and they want to have a career in physics. It is very important that we take them to a journey of where are we today as far as computing is concerned. First of all, let me just tell you that at the moment I am sitting in Shimla. I have been a former professor of physics at Himachal Pradesh University, and currently I am also uh, working for IAPT as its president, that is Indian Association of Physics Teachers, which also allows students to become its members. Student membership is available. Maybe during this set of lecture, at one point, I'll try to take you to the IAPT website to become student members. On the screen, you are seeing two pictures, one on top and other at the bottom. The top is an iconic picture of Simla's uh, Protestant church, and at the back of it is Jakhu Hill, and just on the left hand corner, there is something which was a hub of students at some point of time. This is actually a library. I have sat in this library many a times during my student days. Going to the library has been a great experience and opportunity, I would say. And at the bottom, you are seeing uh, one very iconic building of Himachal Pradesh University campus, where I have spent a lot of time as a student and as a teacher, and I'm still part of it as alumni of the university. This is the library building once again, which is one of the biggest libraries in the state. And on the right hand side is our physics department. I have worked here in this building for teaching, research, and many other opportunities which university offered. And here is a beautiful garden just next to these two buildings, where it is very pleasant to sit down and enjoy sun during winter. So, with this brief introduction, let me just take you to how this journey started in India. On the screen, you are seeing two titans of Indian science. One is Professor P.C. Mahalanobis, and other is Homi J. Bhava. To your surprise, let me tell you that Mahalanobis was by training a physicist, but later he started a completely new venture in the country of establishing Indian Statistical Institute, where they actually felt the need of having a computer. So they were into making a computer also in India, a what is now called Make in India program. Homi J. Bhava by training was initially an engineer turned fifth. May I switch off mic of the, yeah, I hope you will take care of it and there will be no disturbance. So, Homi Bhava started with a mission of becoming a physicist, and he made a change of his course of studies from engineering to mathematics. He did engineering because his father wanted it. He became a physicist because he wanted to become a physicist. So we are lucky that we had these two titans of Indian science as physicists. Homi Bhabha also realized the importance of having a computer in India. And you know that Bhabha Atomic Research Center and its associates is a great indigenous effort to provide self-reliance in critical technologies. This is very, very crucial to appreciate and understand. Now, when we think of computer systems, we started with mainframe computers, parallel virtual machines, then came desktop personal computers, which were converted into laptops. Then now these laptops have been converted into palm tops, and your mobile is nothing but a very, very powerful machine which is in your hand and is in fact a computer only with very interesting interfaces attached to it. Then today we are talking of clusters of computers which may not be available right on your desk, but you can link to those clusters via internet. Now, the first mainframe digital computer was built in India by TIFR, which was actually started or initiated by Homi Bhabha for doing research in fundamental sciences, physics, mathematics, chemistry, biology, and now it is a very, very big institute with very many branches, but focus is mainly on what you call basic sciences. Now, for this purpose, for making this computer, Bhabha decided to build a team. So what was done was, dear students, you are exactly at this kind of a stage. He gathered 6 people with an MSc in physics and specialization in electronics. Imagine, at that time, we used to really study electronics as a special course in MSc programs of physics. Even now we do that. And they were given this task of assembling a mainframe digital computer. You can see in the picture, Pandit Jawaharlal Nehru actually inaugurating this TIFRAC, or what is called Tata Institute of Fundamental Research Automatic Calculator. Now see the names, automatic calculator, not say a personal computer or something like that. And in fact, there is a very interesting link which is available on the internet for this development of TIFRAC indigenously in the country. Now, if I look at this TIFRAC and try to compare what kind of first generation computers were available outside India, you will find that in the first column, there are certain elements which are given like date started, date commissioned, hardware in central processor, memory type and capacity, memory cycle time, word length, logic scheme, and at subtract time, multiply division time, input, output, and total power consumed. Now, if you look at this, we were, in fact, quite an early starter in making these pilot machines in India. IBM started in 1950. Institute of Advanced Studies, Princeton, started it in 1946, and TFR started it in 1955. And by 1956 November, it was commissioned. It was the pilot machine. Then it was converted into TIFF rack. That is the machine which I was talking about. It was initiated in 1957, and in 1959 it was completed, and 1960 February it was commissioned. And to know that how big this machine was, it had 2,700 vacuum tubes, 1,700 germanium diodes, 12,500 resistors, and ferrite core memory of 2,048 words. It was a 40-bit computer only, and it was an asynchronous machine, and it used inputs as paper tape, output as teleprinter, CRT, that is cathode ray tube for character display, and a magnetic drive was added later, and it consumed about 20 kilowatts. Try to imagine 20 kilowatts. It's a huge energy. Compare it with the energy which is being consumed by the computer on which I am sitting and talking to you. It is very, very small. Okay, fine. Now, India, in fact, later thought of bringing a computer from abroad. And first digital computer of that kind came in IITs. It was called IBM 1620. And the main emphasis of this program was to teach programming. Actually, I am seeing some noise in the background. I don't know why it is there, but it is definitely there. And let me see whether there is some other system which is on nearby. Please check that there is no system on nearby, so that there is no echo in it. How many people are there as Arun, please mute your
Okay, sir.
meeting host. Yeah, I think now that noise will go away. I'm coming back to you, don't worry. I will be back immediately. So as I was talking about this, the first digital computer which was imported in the country was for IIT Kanpur. And it was basically there for teaching programming. And try to see that how big this machine was and how it was actually taken inside a building. A complete story of computers in India have been provided in a very interesting book, Against All Odds, the IT Story of India, in which there are some very interesting people who are writing it. One is Gopala Krishnan, who was one of the founders of Infosys itself. Now, this is the time of early 70s. And the kinds of machines which were available to us then were IBM 1401, IBM 1620. This is the one which was there in IIT. And then, VAX workstation, DEC workstation actually also came. And they used punch cards, card readers, paper tapes, magnetic tapes, and terminals. So you can always see this kind of a machine sitting next to the mainframe machine, which was for punching cards or for punching tapes so that we could give input to the machine itself. Imagine how cumbersome it must have been to work in this kind of an environment. And it was a completely a specialist job that you needed to be a specialist, a system analyst, or a programmer. And as a programmer or a system analyst, you were acting like a bridge between the machine and the users like physics people. But slowly and steadily, by the end of the 70s, the scenario was actually changing. And this also opened up many possibilities in physics. You know that physics is done mainly in two ways. But I think today, if somebody asks me, then I will say we do it in three ways. One is theory, other is experiment. But then we have added another dimension to it, which we call as theoretical experiments. This particular program in which you are participating is actually nothing but doing theoretical experiments, or sometimes what we call simulations, or what we call modeling, the title of this particular course itself. Now, experimental theory is what? For this, actually, we need to look at the following two things. What the experimentalists can measure, the theoreticians cannot calculate. That is a dilemma. Second, what the theoreticians can calculate, the experimentalists cannot measure. So, how to remove this kind of a dilemma was one of the fundamental things in developing theoretical experiments, or what you call in physics now as computational physics, which has got very many branches now. This particular course will offer you an exposure to density functional theory, which chemists claim that we created it, and physicists also claim that we created it. Actually, man who actually let this happen was working in physics, but when it came to giving a Nobel Prize, he was given a Nobel Prize in chemistry. Now, when I was actually preparing this particular talk, I talked to one of the persons who was living those moments at IIT Kanpur. In the picture your screen, you are seeing Professor D.G. Kanhare. He's a very good friend of ours. Arun and I both know him very well. And he was the one who actually started using computers for doing the kind of calculations which you are going to do on a laptop today. To tell you very frankly, he was working in solid state physics, and the task was to solve Schrodinger equations for calculating what we call electronic structure calculations. That is what you are going to do in this particular course also. And in those electronic structure calculations, if somebody asks me, what is the kind of numerical method which we use? Let me tell you that process is nothing but doing Schrodinger equation by matrix method, and the matrix which you get to get its eigenvalues, it involves what we call diagonalization problem. And the machine which was there in IIT Kanpur, that was capable of handling 100 cross 100 matrix. Huge matrix it is. But today, the kind of calculations which you are going to do, you will find that your laptop will be capable of doing much bigger diagonalization of the matrices. And he told me that there was a queue system to wait for your job to be put as deck of punch cards. So it was like, when you write a program, after writing it, you will punch cards, and then those punch cards would be handed over to the computer people who are manning the machine, and then the job will run, output will come, and sometimes it would happen that we will realize that there was some error in the punch cards, and you were supposed to once again correct that error, bring that deck of punch cards again, and see that what the solution is. And as Professor Kanhere told me, that during that time there were two places, one at IIT Kanpur and other at TIFR, where a lot of interest was emerging in what we call as band structure calculations. I hope you know, and you must have heard about band structure also. Every +2 student knows about it, that semiconductors, metals, insulators, if we try to look at their band structure, we will be able to make a distinction between which one is a semiconductor, which one is a metal, which one is an insulator, which one is a semi-metal, and so on. And when we do these calculations, as I was telling you earlier, we are doing nothing but electronic structure calculations. And seeing the limitations of the machines in IIT Kanpur, most of the groups working in solid state physics labs used to go abroad in US, UK, and other European countries to use their computers. Now, look at it. In 70s, to do computations, we were physically transporting ourselves to a place where the computer was there. Today, I don't need to transport myself from one place to another physically. Rather, I can access those computers from my desktop thanks to the internet highways via which this kind of a collaboration is possible. And most of the people during at that time who were working, they were basically interested in availing better and better computational facilities. Now try to see that what is the role of an educational institution in creating such facilities. And let me put it like this, dear students, you are very lucky. You are in 21st century. You don't need to look very far for these opportunities. They are already available to you in your campus, rather in your home, if you own a laptop. Let me come to 80s now. It was in 80s that IBM produced its first desktop personal computers. And fortunately, it was in 1984, a very young prime minister came on the chair. He was Rajiv Gandhi, and he started talking about the role of personal computers in our life, in our educational institutions, etc., etc. He was young, dynamic, and was ready to plunge into the new technologies. I was also, working at that time in St. Bede's College, which is at the far end of the city, which stretches itself from east to north, east to south. And St. Bede's is in the east, and in the southwestern corner, we were in Summerhill. My aim used to be to come from St. Bede's whenever I was free to visit university and do my research. On the way, there was a stall where magazines used to be sold. And this was one of the first magazines, computer magazines, which came, called Computer Today. You can see this in this picture, this Computer Today issue, in which they started teaching 4 languages. Remember, we didn't have a computer. But once you learn these languages, you can at least think of writing a program very easily, because now there was no punch card which was needed. You could sit down on your keyboard, connect it to your desktop, and start typing in an editor the program and run it and see what is the output. And the languages were BASIC, Pascal, C, and Forth. I was very much interested in learning BASIC, and this was one of the initiations into learning languages as far as my personal journey of learning computers is concerned. This set of lessons I still have with me, and which I have kept in a bound form as a very precious memory of that particular era. Now came what we call as 2, 3, 4 different kinds of things. We have we had programmable calculators. And now you can see here on the left hand corner a calculator. This is my personal programmable calculator which I purchased before I could go on this PC. And the need for this was because we wanted to do some calculations for our research work. And we found that those small calculations can be very effectively done with the help of this programmable calculator. The language was very close to BASIC. This was that first PC which came, and it had a hard disk, a RAM, a keyboard, a what you call visualizing screen, and so on. But before this, this was actually called a PC-AT, AT. Whereas there was another machine which was called PC-XT, in which there was no hard disk as such, in the sense that it was too small to take care of an operating system also. The memory was very costly at that point of time. So you used to actually take an operating system which was available on a floppy disk, and you will put it in for booting. System will boot. Then you can write, say, some programs, etc., and save them on another floppy disk only. When I purchased my first computer, there was a hard disk available in that computer, but you will laugh at it when I will tell you that how much was the hard disk's memory. It was just 40 MB. Can you imagine it? With that 40 MB memory in the hard, how much I could have stored. But the best part was this, that we didn't have that heavy pictures and the videos which needed lot of hard disk or memory for running those itself. The RAM was just 4 MB, which is again very small, which is called random access memory. It is a kind of a small place where while things are running on the computer puts certain things which are temporarily created during that process. And slowly and steadily, things started improving. It was between 1993 and 2023 that we started with Intel's Pentium series. And all these pictures which you are seeing here, I hope you are able to see the cursor. They are the pictures of those Pentium, processors which were used in different periods of time, like between 1993 to 2003, then 2003 to 2006, 2006 to 2009, 2009 to 2013, and so on. But Intel's Pentium CPU or what you call central processing unit, is still running in our computers. When I was talking about that floppy diskette, here is the floppy diskette, 4.5-inch floppy diskette. And when we were actually using these kinds of computers, we never had programs like Windows. There was no visual interface between the machine and the person who was working on the machine. We used to type on the terminal whatever we wanted to do, open a file, type down our program and run, but no Windows interface was available. It was only in late 90s that we started having Windows and higher versions of that. My computer today is using Windows 11 version. I was having this machine, Acer, as the first laptop in the university. In fact, it was bought in University Institute of Information Technology, where I initiated that program on BTech in information technology. I and Arun, they started using this kind of a computer with a very different operating system than DOS or Windows called Linux. And for doing computations on laptops, you will find that this is a kind of a default operating system. And it works very nicely. It is freely available. You don't have to pay money for it. Whereas for Windows, you have to pay money. You have to pay even for many other proprietary softwares to run on Windows money. Whereas in Linux environment, particularly for scientists and faces, you can run those without any kind of a cost. Now, look at this. This is my laptop, this what you call mobile, A53 5G. 5G enabled mobile, it is there. And uh, this clicks beautiful pictures. You can create videos on it. And you can do very many other things. But let me tell you how you can use it for helping you in computation. You will find later, I will tell you that also, that there are a number of programming languages which are very useful for us while analyzing or graphing data which comes out of huge machines as output. So if we want to visualize that, find meaning that what those numbers, lots and lots of numbers are telling us, we require visualization process also. And Linux has very interesting visualizing interfaces also, which I hope you will learn during this work. Now, let me just take you to a journey that when we try to look at the capabilities of a computer, we actually try to think in terms of how many floating point calculations it can perform for us. Actually, inside the computer, we are all the time dealing with zeros and ones, and we try to do the algebra of these zeros and ones, or the arithmetic of these zeros and ones. That requires lots of floating point operations. Now, when I look at first ENIAC machine, it was 500 floating point operations. And if I look at proprietary IBM machine, it is 500 petaflops. India has recently launched AI-aligned computer called Param Siddhi. And it is quite good in the sense that it has 5.7 petaflops and 210 AI petaflops. AI stands for artificially intelligently tuned computer. Now, during this process, we also started learning programming languages, learning doing physics with the help of these programming languages. And we wrote a few books as a kind of a self-help manuals. One of such books actually was the result of our collaboration with one of the uh, very eminent physics teachers in one of the government institutions. He retired as government SCRT principal, Professor uh, Upendranath Khosla. He was attending a program with us in university, which was a refresher course on computational physics. And he said, we don't have any resource material. So we invited him to join us. And this was the book which came out. This was on disk operating system in writing programs in BASIC. Then we transitioned this to a Fortran version. And simultaneously, we started exploring how to do physics problems on a computer. This book was one of the first books of its kind in the country in uh, early 90s. And there were three people involved in it. One was Professor R.C. Verma, another was Professor K.C. Sharma, and I was also there doing work for them. Let me tell you that when creating the manuscript of this book was concerned, I was able to really uh, what you call uh, word process it on my 40 MB hard disk computer with 4 MB RAM. And we gave a camera ready manuscript as a result of the availability of that uh, computer and the software for desktop publishing. Now, as I have been talking to you, I think you must have been hearing some terminologies like disk operating system, Windows, Unix, Linux, and many other things. And here is a list of such operating systems which are there. I worked in DOS. I have worked in almost all the versions of Windows. We never had the opportunity to work in Unix because these were not available because it was the operating system for mainframe computers. The companies which made this machine was HP, IBM, Digital. Even now, I am using a laptop which is made by HP. And also, simultaneously, there was another company which was floated by Steve Jobs. I hope you must have heard his name because Apple was the name of his company. And he created a computer with very, very versatile graphic possibilities. And he was actually preparing people to look forward to a computer for uh, high density visualization of the pictures on the screen. And then there were some Linux operating systems, Fedora, Debian, SUSE, Ubuntu, and so on. Uh, Arun and I first started working in a Linux environment called Debian environment. I also had an opportunity to make use of a Red Hat uh, version of the Linux environment, which was at one point of time very, very popular. Now, try to imagine when we started, the computers were very, very costly. I spent almost 70,000 rupees to buy that computer, which was almost equivalent to present times 5 lakh rupees. And Bill Gates came as a businessman who was very clever. He wanted money for every resource which he was putting in his computer. And you will notice that this computer, which we are using, say if it has Windows, they may come forward with a message that we are withdrawing our tech support for any kind of problem with this operating system. And you may find yourself high and dry on the road. And that is why lately there has been a great switch over to what we call open source evolution or revolution, whatever you want to call it. Open source actually means that these resources have been created and made available to anybody who wants to use it and doesn't have money in his or her pocket to pay for that. Please do remember this part very, very clearly. But this was a very interesting evolution. Thanks to Debian, Fedora, SUSE, these were all open source softwares. And they had many other tools also available in this operating system. Now the times have changed. We are finding we no longer call solid state physics as solid state physics. We call it condensed matter physics. We also find that we are talking about soft matter. Professor Amarjeet works a lot in this area. When we are talking of material science or computational material science, we are basically talking of condensed matter physics only, but producing materials which can be used for technology purposes, like for building computers. And the kind of hardware which you want to have that requires very special materials. Nanoscience, for example, uh, all these things have really changed over a period of time. When I had finished with this project of, writing that book, that computer which I had bought gave me an opportunity to apply for a Commonwealth Fellowship to go to a person in Edinburgh who had or whose group in that University of Edinburgh in the Department of Astronomy and Astrophysics, uh, what you call as parallel computers, Cray computers. And I had met Professor G.S. Pauly, who was one of the computational physicists there in India twice. Once was in Jabalpur, and second time it was in Jaipur. And when I was to apply for that fellowship, there was a condition that we must talk to somebody in UK who is ready to uh, make us a guest uh, teacher there as the holder of academic Commonwealth Fellowship. And for the first time, I used a Cray machine. And it was this time that I got initiated into what you call DFT calculations. It was in 97, 98. In my university, there was no such facility available except for some desktop computers which were not capable of running any of these programs. So after I landed back here in India in my department, a thought always used to come in my mind that maybe I have just wasted my 1 year there because whatever I have learned there I cannot use. But dear students, remember one thing: learning never goes waste. Slowly and steadily, when we moved into 21st century, around 2000, 2001, 2, 3, 4, 5, we started having very good desktop computers, workstations available to us. And a ray of hope actually arose that we can try to do these kinds of calculations, which I had learned in Edinburgh. But we found that the machines were still inadequate. And the kind of softwares which we were to use, they cannot be fitted on these machines easily. They required huge memory, they required huge RAM as well. In fact, if you try to check in your computer, you will find by default these days a RAM of 2 GB, rather not just 2 GB, more than that, say 16 GB or 32 GB RAMs are coming. And then again, we started, thinking of what we should do. If you look at today's program and the poster of the program, which is hanging in the room where you are sitting, I believe, you will find there is another word written there using Siesta. Siesta is the name of a code which you can run for doing DFT calculations. And what is the advantage of Siesta? And that you should know because you are in a workshop on Siesta itself. The advantage of this is that this software can do DFT calculations involving thousands of atoms. And I was actually informed about this by one of my students who was working in Germany at that point of time. And he said, sir, एक सॉफ्टवेयर आया है, वो कोड है, वो ना चल जाता है पीसीज पे, लैपटॉप्स वगैरह पे. And there was again a ray of hope to make use of my learnings which I had learned in Edinburgh. And Professor Pauly was very kind to give me that kind of initiation into this subject. Now, when we do these calculations, what do we do, by the way? We actually try to do very many things. We can possibly do almost anything which we want to really look at. You can look at uh, crystalline structures. You can look at transitions. You can do ground state calculations. You can do transport properties. You can generate Fermi surfaces. You can do simulations of special kind of uh, materials to check whether they can be used for superconducting sake or not. Ferroelectric is a very hot field where people employ simulations to study the properties of ferroelectrics. There are many other outputs which also come from such machines, which give us a lot of information about very many other areas of physics also, as far as the properties of those materials is concerned. For example, optical properties, which include, say, birefringence or optical activity of that material. Similarly, we can also study phonon spectra, we can also study Raman modes, etc., through these calculations. Actually, I want to caution you about one thing, and that is that please do remember, when we are doing computation on a machine, very big machine, we are actually modeling that material which we want to study. So there are two things which simultaneously happen. One is modeling a material, seeing what are its properties which are coming out because of the model which we are using, and check whether any of these results match with the experiment or not. Do remember one thing, you can do as many things as you like on the computer, but doing physics demands that our outputs of these machines should match with what people are finding experimentally. In that sense, when we try to study these properties, I think we have provided very, very sophisticated computational tools to very, very accurately predict the behavior and the properties of those materials itself. So do remember that when we are sitting in this particular program, what are we actually trying to do and what are we actually trying to learn? Now, as far as Siesta is concerned, we have chosen it because of the fact we don't have much money in our pocket. We have chosen it because we can handle large number of atoms with the help of it. We can study a large number of properties with the help of this code itself. But do remember one thing, the codes are not physical reality. Whatever we do on the computer, it must match with what people are doing in labs or what people observe actually in nature. So when we are talking about these kinds of possibilities, we also find that apart from these electronic structure properties, we can also think in terms of the natural materials which we get in nature and try to simulate them also. Now, what type of materials are available to us in nature? For example, crystallines are available, amorphous materials are available, alloys are available, multi-layers are available, systems with defects. The role of vacancies and stacking faults on the band structure calculations, dislocations, color centers, nanosystems like surfaces, wires, dots, and so on. And also, you will be able to see that till date, we are working from our homes as far as this kind of an activity is concerned. Now, what are the other systems where we find that what physics people have actually mastered that these things can be used? One is chemical reactions. Other is we can study biological systems, for example, proteins. We can study nuclear systems. By the way, let me tell you that the first atom bomb which was thrown on Hiroshima and the second one which was thrown on Nagasaki, they were first simulated on a computer in early 40s of the 20th century. I hope you are getting what I am trying to uh, convey you. Uh, do remember one thing, that what have these computers done for us as far as the study of physics is concerned? It reminds me of Archimedes, who once made a statement about power of a lever, first order lever. I hope you have studied levers in your plus 2 or in class 10 or 8 somewhere. And his statement used to be, give me a lever long enough and I will move the world. If you change lever with computer and long gets changed to big enough, you will find it becomes a very, very meaningful statement, which actually, in a sense, summarizes the power of computers in doing science, in our case, physics, but we have a lot of overlap with chemistry and so on. So, this is very, very crucial. And when I was actually talking about this list of systems, uh, now I'm finding that we can, with the help of these calculations, study corrosion behavior of a material, mechanical behavior of a material. These days, people are talking about what you call uh, the materials of future. They require a lot of understanding uh, on a computer itself. Then circuit analysis, network analysis, we can draw diagrams, PV diagrams, for example, generate equations of state. We can think of working in geophysics as a geologist. I can think of making use of these softwares to make predictions about uh, geographical places where we might be sitting. Now, what are the computer codes which are very popular? One is WASP, costs around 4 lakh rupees. Then comes EBNIT and Quantum Espresso. They both are free. And these two softwares, EBNIT, okay, is free. Quantum Espresso is free. Siesta is free. Decapo or ADF is free. But CastStep, this was the software which I used in Edinburgh for doing simulation of a very big, what you call geological rock. And we can also study what are known as non-equilibrium transport properties of the system. Now, apart from this, you will find there are different kinds of codes which are available to us. Now, if you ask me what kind of code siesta is, I'll say that it is pseudo-potential code that we make use of in our model to run a system, a pseudo-potential. And if I'm not getting that what is the need, we will find it difficult to really survive also. So these are called pseudo-potential codes. And I don't have much time, but maybe later in my lectures, I will talk about this also a lot. So now if I look at computer codes, you will find all these LMTO, FPLMTO, etc., are available to us on the fingertips, you can call it. Then we also have codes of different varieties. There are certain codes which are very accurate, but make use of genetic algorithms. Similarly, other codes, how they are aligned, is also very interesting. Now, I would like to caution you on one thing more when you are actually trying to learn what you call uh, modeling and simulation. And that is that we have to work with those computer codes which are very powerful to do a simulation of the kind of system which I studied in Edinburgh. Okay, so there are lots of codes available to us, and we can also think of making use of those. Now we have another set of codes also, which are very useful for molecular dynamics calculations, like ab initio calculations, and so on. So these computer codes are going to be very useful. These are additional softwares. You can purchase these. These are not very costly as such. Now, why computer? The question comes here. I'm trying to convince you that if we want to do physics in frontiers, computation is part of that job. Remember one thing. When we started with computers, there used to be a single computer followed by a queue outside the room where this computer was sitting. Okay. एंड उस छोटी जैसी मशीन को यूज करने के लिए 250-300 लोग हमेशा क्यू में रहते थे. ओके, बट लेटली वी हैव चेंज्ड आवर pathway, and we know that in what way we have to reuse use what. And you can see here that how big matrix manipulations it can be. 2 crore 50 lakhs. This is huge amount which is there. Now, I am at the end of my lecture as far as this part was concerned. I think I was very lucky that from time to time I was exposed to the possibilities for doing physics on computers. And one of the earliest workshops which I attended, in which uh, simulation was talked about, it was actually an Indo-French International School of Statistical Mechanics run by Professor R.K. Kalia. And it was in the physics department that we got the first branch, or the first uh, version, or the first grant for the purchase of PCs which were booted with the help of floppy disk. ये हमारे डिपार्टमेंट में आई थी ये मशीनें. Then we also had a refresher course in which computational condensed matter physics was actually put forward and studied. You can see Professor D.G. Kanhere's name in it. Professor K.C. Sharma's name in it, Professor Sanjay Puri's name in it, and so on. Now, by 1994, we were ready with a refresher course in computational physics. And in 1995, we established a far, far improved computer center in the physics department, which was called Nodal Center for Computer Applications in Physics. When I will make this statement, you will laugh at it. And what is that statement? That statement is that though computers were thought of by companies which charge a lot of money, here this model of running a refresher course in computational physics can be very easily adopted. Then 97 to 98, I had Commonwealth Fellowship. From 2000 to 2008, I was director, University Institute of Information Technology. And it was during this period we also met Professor Sushil Aulat, who was authority in band structure calculations. Very humble, and he also made us learn very many things newly. He was very passionate teacher. Also, we find that in the country there is a lot of talk about computations. And we are finding that a material science group has been created for posting the receipts, etc., which are there with me for some task. Okay, so all these things can come together. What we can do with the help of this, create computational physics teaching, have an HPC lab with 128 cores. Today in the physics department in Shimla, there is a very powerful machine with almost 128 cores called Shavak. We have a licensed software called WASP. We have a very, very costly atomistic toolkit available in the physics department. I wish if Professor Amarjeet can really hold some kind of a program in Shimla in which access to the Shavak can be given for running the programs which students will learn. Now, if you ask me what kind of things which we have studied with the help of these kind of developments, magnetic systems, chemisorption, liquid metals and alloys, quantum dots, you name anything which is being heard as a latest technology, you will find that it goes there as a footprint of physics only. Okay, so these are some of the systems which we have studied. So where are we moving right now? We find that one of the best things which happened in the country was establishment of CDAC, which is supposed to create the facilities for computation by designing new computers. Param Siddhi is one of such efforts. Param 8000 is also one of such possibilities. Earlier I said that memory was very costly in a computer. Today, if the cost of the things have come down, it is because of one very, very uh, what you call motivation, and that is to provide access to all these facilities throughout the country without any barriers. So there is a national program on superconductivity which has been launched. It has created what we call as Garuda Grid. It is one of the top class computers available uh, with whom in Delhi. There is one very interesting place where we have very interesting facilities available to us for doing simulations itself. We have also using computers started supporting certain very, very specialized tasks. Like, for example, supercomputing in Indian languages. There is a lot of talk about, providing spaces for doing big calculations right into the computer centers. And Government of India has initiated a budget of around 4,500 crore as National Superconducting Mission. And under this program, the Government of India empowers uh, an ambitious target of installing more than 70 high performance computing facilities in the country. UVA 1 and UVA 2 are, and naturally, AI and machine learning are also two things which are very, very interesting. Now, I want you to meet one very motivated kind of a person. Who must have been this motivated person? Maybe you know his name. His name is Vijay Bhatkar, and he is considered the father of Indian supercomputers. And in fact, he was invited by Rajiv Gandhi to think about this kind of a stage. So when he met Rajiv Gandhi, he asked the question, can we do it? Can we have a supercomputer? So the reply of Vijay Bhatkar was, I have not seen a supercomputer as we have no access to some supercomputers. I have only seen a picture of the Cray. But yes, we can. Try to mark these words in the end. Yes, we can. And then Rajiv Gandhi asked him, how long will it take? And his answer was again very interesting, that it will be less than it will take to buy a Cray for India, because there were lots of sanctions which were there in India because of the nuclear, test blasts. Then Rajiv Gandhi asked him how much money it would take. And he tried to give a guess on that the whole effort, including building an institution, developing the technology, commissioning and installing India's first supercomputer, will cost less than the cost of a Cray. तो ये देखिए क्या बात होने लगी अब. इन्हें कहा कंप्यूटर चाहिए, क्या बना सकते हैं? तो इन्हें कहा हम बना सकते हैं, तो क्रे जैसा बना सकते हैं, यहाँ बना सकते हैं. मगर आपको क्या करना है? हमें वो प्रोवाइड करने हैं मींस जिससे सब हम कुछ ये कर सकें. And then Rajiv Gandhi asked him how much money it would take, right? And I have not written those figures here. It was much less than what you call 1 crore rupees. Now, this Garuda has a nationwide grid. And this picture, I hope you are able to see this picture. It provides linkages to various airports in the country to make travel easy. Now, I would like to really, at the end of this small dialogue which happened between Vijay Bhatkar and Rajiv Gandhi, I would like to acknowledge very many people with whom I have interacted throughout my teaching and research career. The these first column which you are seeing is the column corresponding to people whom I know and who are passionate about computational physics, and with the help of whom I really learned a lot as far as computing was concerned. And here is the list of people who have worked for their PhD with me. Already you are having Dr. Arun Kumar sitting with you, and Dr. Surjit Chandel sitting with you. And they have got all sorts of codes available for running the show. Okay, you can be in touch with these people also if you want to learn more, because they are passionate about it also. These are some of the references which I have used, and I hope you can also go on the internet and find large number of such uh, references. And Pakistan uh, has done what? वो तो चोरी चोरी करके लाते हैं. What India does is India अपने आप इन चीजों को प्रोड्यूस करने की कोशिश करता है. So this is a difference between approach of our country and of some other countries which are trying to be at par with us. It's a very big challenge. It requires human resource and the confidence of Vijay Bhatkar so that things may materialize. So I think I am ending here, and thanks. If you have any questions, you are free to ask me. I hope you have enjoyed this journey. So I am stopping presenting, and I hope you are able to see me now. I am also able to see you. I hope you didn't feel like going to sleep in the whole lecture, but it was a journey worth remembering and appreciating. Thank you very much. Any questions? Raise your hand and ask.
Thank you, sir. Any question?
Yeah, Amarish ji, please.
Okay, sir. Thank you very much for this very enlightening lecture. And we have, from the very beginning, we have seen a lot of things which I did not know. I just would like to know one or two things.
Yeah.
One is this DFT. This DFT is a generic thing which is running behind all the codes that you discussed, like Abinate, Quantum Espresso, CSR, and all.
Hmm.
And so why this, I mean, basically, we have different kind of packages, or we say software packages for running. So it's because their approach is different, or we can do different things with them, and DFT is at the heart of it.
See, one thing we must remember, Amarish ji, you can't just come in front of the camera. You are just hiding yourself on the side. Oh yeah, yes. Yeah. This is the best place to stand. Your question is very, very relevant, because when one sees the list, it is like going to the shop of a sweet maker. There are so many sweets available to us. And if we'll try to ask what goes in those sweets, there are some common materials. Like sugar goes into it. Yes, हलवाई की दुकान बेसन के बिना नहीं चलती है. हलवाई की दुकान में आपको तेल चाहिए. But if you go in south, in the sweet maker shop, if you come to north, if you go to east, everybody is making sweets. The background theoretical understanding remains the same, but they create magic out of that depending on what they want to really eat. This is small analogy which I can give you. Now, in the context of these codes, you will find that density functional theory was a kind of a outstanding contribution to help us see that how we can run these things on machines. Because density functional theory actually reduced a 3n many-body problem into 3-dimensional many-body problem. That was the best part of it. And that brought the computational cost of working on the computers very much under control. And we were capable of running these things on a computer. Now, it is not that we make use of DFT in one way. There are a number of ways by which we do. You must have seen in the presentation, I classified these codes into pseudo-potential codes. I also specified all electron calculation codes. And you will find that seeing the potential involved in the system as a pseudo potential is a kind of an approximation, which is a very intelligent approximation, where what you do is you just forget about the core electrons and still you are able to do the calculations. Then there are lots of approximations which have gone into arriving at density functional theory itself so that things become manageable. So these are some of the aspects which we must really try to keep in mind. And that is why the variety of codes is there. Now, if you ask me, I think I will take your question like this. How did I choose Siesta as one of the codes out of such a big possibility? Idea was very simple. We had limited computational facilities, and we found that Siesta fits in very nicely into it because of less memory requirements for running the code itself. Whereas if you try to run WASP, which is actually not the kind of code which Siesta is, it is a plane wave code, not an orbital code, where we actually look at electrons in the form of those uh, orbitals. It is a plane. We see electrons as nothing but the plane waves. Here we see everything in the terms of orbitals, and the cost of computation actually comes what you call low. So this is how we decide that what we have to choose. There are certain codes which are very good for doing one kind of properties because they are tuned to do those kinds of things. They have those kinds of elements into those codes which require the what you call supplementing of DFT with additional information. Like for example, when you want to do magnetism, you will hear those things here that we are not very happy with, say, local density approximations only. We want LDA plus U. So what is this U? This U is corresponding to the part which magnetic systems have to really take care of. Other give a detailed answer to your question that how we choose it depends on your taste, what you want to study. It depends on what is your theoretical interest. Uh, if you will look at our group's work, you will find that our choices of even picking up systems was such that we were able to manage these things within a very limited time with very limited resources also.
Okay, so thank you. I will also see this, as an opportunity that you can begin from somewhere which you find the easiest and which is workable, and then you can expand depending on your budget and your type of problem you are choosing. So this is
Yes.
also an opportunity. I will ask just one more small questions, and I see that there are questions which are coming online. So Arun, you will pick
Yes.
up
I can see those questions. Let me really go to the question. There was one question which was uh, sent by Neeraj Thakur. Is DFT limited only to calculations of the ground state properties? Answer is, for the time being, I would say yes. The kind of code which we use, Siesta code, it is for ground state properties, but you can also enhance these codes with special supplements once again, so that you can bring things so that you may go above the what you call 0 degrees Kelvin, which we consider as the ground state of the system itself. So there are possibilities, codes are available for doing that also. I think if you will explore WASP, you will find that there is a possibility of doing what you call beyond ground state properties also. Now, when we are talking of transport properties, we are going beyond ground state properties itself.
Okay. One is just a question of principles of DFT. Like, as I see this here, the problem in condensed matter, we would work at the length scale of angstrom. We are talking about electronic structure where we have orbitals and atomic orbitals size of angstrom. My question is, can in principle DFT be scaled up or scaled down? Can we go inside the nucleus using DFT? Or can we scale up the things in principle?
Actually, when you are talking of scale, when I am actually talking of this localized orbital and plane wave codes, I am not really talking of scale in terms of dimensions, okay, or the size of the systems. It's not like that. The scale is in terms of finding something being done efficiently and reliably.
Yes,
We
yes,
cannot
yes.
really have efficiency but no reliability.
No, your scale I understood. My question is particularly the land scale of, let's say, nucleus, or of course above. I think as I understand, as we are working with atomic potentials, probably it may not be a right question, but can we go inside the nucleus and have the DFT at that level when density of the nucleus is varying, something like this?
Yes, if you ask me that what kind of systems we are using, let me look at it like this. If I want to do the study of a molecule with the help of DFT, I can do. If I want to study a protein, I can do that also in principle. Why I would say that I would not be able to do that, because my means are limited. We find that the cost of running those systems is very, very high. And for example, biology people, if they are told that you please run these things, they will never opt for DFT, because proteins are very, very complex systems. Very large number of atoms are involved in that. And they prefer to have what you call as molecular dynamics calculations, where they use a potential which takes care of very many inherent properties of the system itself. So this is a kind of a compromise which people make in looking at the scales at which you are using or you are trying to study the things.
Okay, so thank you, sir.
Thank you.
May I answer something?
Yeah.
Actually, people are using density functional theory also in nuclear physics. In the beginning, when I started to read the DFT, then I read the theoretical formulation from a nuclear physicist. You can also search paper on the archive also. And another question regarding that, is DFT limited only to the calculations of the ground state properties? So we can use CSA for doing band structure calculations by using molecular dynamics, temperature dependent, and we can calculate temperature dependent band structure also. And even we can also calculate the excited state properties using the TDFT. Recent version of Siesta will do that.
In fact, you have rightly mentioned that sometimes when you have a property in mind, whether it is ground state only or it is say temperature dependent, or you want to study excitations, etc., etc., DFT alone is not enough. For example, to study excitations, you will have to go to time-dependent density functional theory. Okay, now this TDFT codes are also available where you can go and try to run those things. But again, with time-dependent density functional theory, the cost of computation actually goes higher. So again, you come down to a situation where you say, okay, let me confine myself to the ground state properties only. But the way computational facilities are enhancing in the country, there are possibilities of logging into those kinds of big machines where these things can be run efficiently and easily because of their big RAMs available, the kind of number of cores and the parallel computations which you can do. It depends on how you would like to scale your research. So to scale your research up, you have to also go for those kinds of means which are available on the cloud for sharing. So it depends how you want to really look at it. I hope I have given you the answer.
Correct. Any more questions? So on behalf of Physics Department, Government College Nagpur, I thank you, Ahluwalia sir, for giving a present, past, and future of computational facilities in our India, and especially how our group SD functions unique grow. So I thank you from the floor of my heart.
Good. Thank you. So may I log out now?
Yeah, right.